Hello everyone, my name is Laura Dodds, and today I am very excited to tell you about our work on non-line-of-sight 3D object reconstruction via mmWave surface normal estimation. This work is in collaboration with my co-authors, Tara, Kai-Chen, and Fadl. Now, we all know that non-line-of-sight mmWave 3D reconstruction is an important problem in our community. So in this project, we aim to answer the following question. Can we enable high accuracy, non-line-of-sight 3D object reconstruction with mmWave signals? For example, can we reconstruct an object which is hidden inside this box? In this case, a hidden spoon. Today I'll tell you how existing mmWave reconstruction methods are unable to produce high accuracy 3D reconstruction, and instead produce something like this. I'll also tell you about our new method, mmNorm, which is able to produce much higher accuracy 3D reconstructions. As you can see, it very closely matches the ground truth shape of the spoon. Now, this new capability of high accuracy, non-line-of-sight 3D reconstruction has many applications. For example, it can be used in robotics in order to find and retrieve missing items, or in shipping and logistics in order to identify mispackaged or broken objects. Or we could display these 3D reconstructions in an augmented reality headset to truly augment our human perception. So today, I am very excited to introduce mmNorm. It is a new and highly accurate method for 3D object reconstruction, leveraging entirely first principles-based approach. This means that it doesn't require any training data and can adapt to any new object. It introduces techniques for mmWave surface normal estimation and mmWave structural isosurface optimization. And it achieves a significant qualitative leap in reconstruction accuracy over existing state-of-the-art methods. Now, before I tell you how mmNorm works, let me first start by telling you how existing methods perform 3D reconstruction. Now, for the most part, we as a community have been performing 3D reconstruction in the same way for decades. It started when we wanted to reconstruct large-scale scenes like this one here. As a community, we've been attaching radars to airplanes or satellites and having them fly over the scene, continuously collecting measurements to form a synthetic aperture. The same airplane can then fly over the scene multiple times, extending our synthetic aperture into a 2D synthetic aperture. This allows us to measure the range, azimuth, and elevation to different reflectors in the scene, which we can use to produce a 3D SAR image. Now, with this, we can generate a 3D point cloud, which for this scene might look something like this. And when we wanted to move from these large-scale scenes to much smaller objects, we followed almost the exact same approach. For example, to reconstruct a mug like this one, past work has attached a radar to a robot or linear stage and used it to move the radar, again continuously collecting measurements to form our 2D synthetic aperture. Once again, this can be used to produce a 3D SAR image, which can be used to generate a 3D point cloud. But this time there's a problem, which is that unlike before, where we were trying to reconstruct massive mountain scenes, we're now trying to reconstruct a tiny mug. So that means that our reconstruction quality is severely limited by our SAR resolution, which in this case is limited by our commercially available bandwidth. Let me show you what I mean. I'm going to show you a real-world result which we collected from this mug as a 3D point cloud. As I overlay this point cloud onto the mug, you'll see that we're not reconstructing a single surface of the object, but instead our points are spread across a wide volume of space due to our limited resolution. So as you can see, these existing methods are really unable to produce high-accuracy 3D reconstruction. I mean, let's be honest. If I showed you this point cloud here, could you even identify it as a mug? Now, beyond these first principle-based methods, there's also been some work in machine learning-based methods for 3D reconstruction. These methods take mmWave data, pass it through a model to perform a 3D reconstruction. But the problem with these approaches is that they require a significant amount of training data, which is simply not available in the mmWave domain. So instead, these projects typically operate on a very small subset of objects. For example, only reconstructing cars or only reconstructing human bodies. So as you can see from these two, we really need a fundamentally new approach for mmWave 3D object reconstruction. So what can we do? Our idea is not to leverage the 3D SAR image for reconstruction, but instead to directly estimate the curvature of the object. We're going to do this by estimating surface normal vectors of our object. So going back to our example of a mug, we're going to estimate a surface normal vector which is perpendicular to the surface at that point. And if we can estimate these vectors across the entire surface, then we can trace them back in order to find our overall surface. Now let me tell you how we translate this high-level idea into practice. Remember that we don't know in advance where our object is located in 3D space. So we're going to start by estimating normal vectors for every point in 3D space. This produces what we call a surface normal vector field. But this creates a problem, which is that this normal vector field actually defines multiple valid surfaces. So for example, this vector field here could represent this surface shown in purple. That's because all of the arrows in this vector field are normal to this surface. But it could also represent many other surfaces, such as these ones here. So how can we know which of these surfaces is the correct surface? We start by deriving a single unifying function, which we call a relative sign distance function. This function captures all of the ambiguous surfaces in one function through its different isosurfaces, which are surfaces of constant value throughout the entire 3D function. We can then use this function in order to formulate an isosurface optimization problem, which allows us to select a single surface as our final surface estimate. Now let me start by telling you more about our normal field estimation. For simplicity, I'm going to explain this concept in just 2 dimensions, but I note that all the concepts here can be easily extended to 3D. Now, our normal field estimation relies on the following important property, which is that mmWave signals experience primarily specular or mirror-like reflections. So for example, if we consider just one antenna in our aperture, it's going to send signals in many different directions. Some of those signals will travel from the antenna, off the object surface, and away from the radar, never to be received. Whereas other signals will travel from the antenna to the object surface and back. These are the signals which will be received, and what's important here is that this happens primarily when the surface normal points directly towards our antenna. Now this is a very important property, which is that our antennas are primarily going to receive reflections from points on the surface where the surface normal points directly towards the antenna. And this is the property that's going to allow us to estimate our surface normal vectors. So let me now switch gears and tell you a little bit more about how we do this normal estimation. To estimate our normal vector field, we need to answer the following question. At a given voxel, what direction is our surface normal pointing? For example, to estimate a surface normal at this voxel here, our normal could be in any possible direction. So now let's say we collect an aperture of measurements, and let's say that at least one of these antennas receives a response from this voxel. Well, that means that we can immediately eliminate many of the possible directions, such as these ones here in red. This is because none of these directions point towards any of our antennas in the aperture. So as I was saying before, due to specularity, these normals simply cannot produce reflections towards any of the antennas in the aperture. And this is great. We've now eliminated many of the possible directions. But can we do even better? Can we figure out exactly which of these directions is the direction of our surface normal? To tell you how we do this, I'm going to start by showing you an example, where we have a surface pointed in this direction. If we follow the surface normal, we see that it's pointed directly towards this antenna here. That means that this is the antenna which will receive the strongest reflection from this voxel. Now the neighboring antennas might still receive some weak reflection, and then the antennas next to that will receive an even weaker reflection, until eventually the antennas will receive almost no reflection. So what we can do now is we can allow the reflection amplitude of each antenna to act as a vote on the direction of the surface normal. So for example, we give each antenna a vote, V1 through V7, and we weight the votes by the reflection amplitude of that antenna. Now we can construct different possible normal directions, pointing from this voxel towards each of our antennas, and we'll weight these by the strength of each antenna's vote. Now this is just one example, so let me show you a second example, where we're going to use the same aperture, but this time have a surface pointed in a different direction. Again, if we follow the normal, we'll see it's pointing towards this other antenna, so this is the one receiving the strongest reflection. And again, the neighboring antennas will receive weaker and weaker reflections, so we assign each one a vote relative to its reflection amplitude. Once again, we construct possible normal directions, weighted by the strength of each antenna's vote. Now, to compute our final normal estimate, we can combine all of these votes together through a weighted sum using the following equation. Now, for those of you who might be familiar with mmWave imaging, you might be wondering what reflection amplitude we use to act as our vote. And for this, we use the reflection amplitude arriving from this voxel in the SAR image. So I'd like to take some time to talk about this in a little bit more depth, and then please just bear with me for one slide, and then we'll return back to the high-level system design. So how do we compute this voting function? To start, I'm going to write out the math for a simple standard mmWave back projection image. We can start by computing individual mmWave images from just a single antenna as the sum across frequencies of the received signal multiplied by the expected signal given the round-trip distance from this voxel to the antenna. And then our overall mmWave image is computed as the sum across all antennas of these individual mmWave images. Now remember, our goal is to estimate how much reflection amplitude is arriving from this voxel in the SAR image for each of our antennas. So what we're going to do is we're going to estimate this by estimating how much each of our individual antenna images I contributes to the overall sum S. To explain how we do this, I'm going to plot some values on the IQ plane. And it's important to note that anything I'm plotting here on the right is not a direction of a surface normal, but instead a complex value on the IQ plane. To start, I'm going to plot the overall mmWave image as a sum across all antennas. At this voxel, this is going to be some complex value with some phase, such as this blue vector here. Now let's look at an individual value for one of just a single antenna, such as this one in green. Since this antenna is in the direction of the normal, it receives a very strong response from this voxel, and therefore it contributes very strongly to the overall sum. That means the phase of its complex number is going to be very similar to the overall sum, such as this vector here in green. Now let's take a second example, an antenna which is far from the direction of the normal. It doesn't receive a strong reflection from this voxel, and therefore doesn't contribute strongly to the sum. So its phase may be in some other direction, such as this gray vector here. So to figure out how much these individual values contribute to the overall sum, we can project them back onto the sum. For example, the green vector will have a large projection magnitude, and the gray vector will have a small projection magnitude. So we can formalize our voting function using the following equation. And what's important here is that our gray antenna starts out with a very large value, but after projection it becomes very small. And this is why when we apply this in our voting function, the gray antennas result in a very small vote. Now we can repeat this voting process at every voxel in 3D space in order to produce our normal vector field. Now remember that this normal vector field actually defines multiple valid surfaces. So let me now tell you more about how we derive our single unifying function. For this, we need to answer the question, how can we capture all ambiguous surfaces in one function? Here we're inspired by techniques from the computer graphics community, where when you have a single surface, you can define a 3D function known as a sign distance function, which is 0 at the surface of the object, positive above the surface, and negative below the surface. Now what's interesting is if you take the derivative of this function, then you end up producing a normal vector field. So inspired by this, in mmNorm, we have a normal vector field, so we're going to produce the opposite operation. We're going to take an integral across our vector field. This produces what we call a relative sign distance function. And what's interesting is, unlike before, where we were taking a derivative, we're now taking an integral, so this introduces an unknown constant offset. So now 0 does not represent the surface of the object, but the 0 could be located anywhere within our function. But what's important here is that we can determine our final surface by finding this unknown constant offset and then taking the 0 level set of the resulting function. We do this by formulating an isosurface optimization problem using the following equation. Unfortunately, I won't have time to go into the details of this part of the project today, but I invite you to check out the paper for more details, and I'd be happy to answer any questions. Next, let me tell you how we implemented the system. We used a UR5E robotic arm and attached a TI 77 GHz radar. We used an Intel RealSense RGBD camera for ground truth, and we measured experiments in both line of sight and non-line of sight using a cardboard occlusion. And we collected experiments across 61 different everyday objects. Now let me start by showing you some of our qualitative results. I'm going to show you our full object, as well as an RGB picture of the surface that we're trying to reconstruct. Then I'm going to show you one of our state-of-the-art baselines. This baseline works by computing a 3D SAR image, and then selecting every voxel in the image above a certain power threshold. Now, of course, you might be wondering, why don't we change this threshold, increase it, to reduce the number of points? But this would result in a very sparse reconstruction, and we would really miss many points on the surface. In fact, this is the threshold which performs the best across all of our objects in the data set. And then I'll show you mmNorm. As you can see, mmNorm is able to very highly accurately reconstruct the surface of the object. It significantly outperforms the state-of-the-art baselines, and it can operate across different objects of different shapes, sizes, and materials. It can even operate in scenarios with multiple objects, such as this case with a fork, knife, and spoon. So next, let me tell you briefly about some of our quantitative results. Here, we measured 61 diverse everyday objects from the YCB dataset, and we measured the distance from each point in our reconstruction to the nearest point in the surface of the reconstruction in the ground truth. Starting with the baseline, it achieved a median error of around 1.4 centimeters. Now, at first, this might not sound like a lot of error, but let's consider for a second the size of the objects we're reconstructing. For example, if we're trying to reconstruct a knife, something like this, it's only around 1 centimeter thick to begin with. So when we add 1.4 centimeters of error on top of that, you're resulting in a lot of up and down jagged reconstruction, which makes it even difficult to identify it as a knife. In contrast, mmNorm operates with only 0.25 centimeters of error, which results in significantly higher accuracy 3D reconstructions, like what you saw here. Now, I'd like to end off today by saying that we truly believe mmNorm marks an important paradigm shift in the way that we think about and understand mmWave imaging and reconstruction. This is evident by the significant advancements in the results of mmNorm. And because of this, we believe it opens up many exciting opportunities for future problems and opportunities for future research. So I'd like to tell you about just a few of them today. For example, I told you today about how mmNorm is an entirely first principles-based approach. This was not to say that machine learning is bad, but rather that we wanted to push first principles to its limits. So we're really excited about the combination of mmNorm and the recent advancements in machine learning in order to solve problems such as shape completion, where we can take mmNorm's reconstruction of the surface of the object and use machine learning to reconstruct the entire 3D object. We also believe mmNorm can enable many exciting novel downstream tasks. For example, could we build a robot which can find and grasp hidden objects without ever seeing them with a camera? For example, directly grasping an item out of this box of packing peanuts. Or can we reconstruct and display hidden objects through an augmented reality headset in order to truly augment our human perception? We're also very interested in whether the insights and results from mmNorm can bring benefit to even larger scale scenes. For example, for indoor scene reconstruction or autonomous driving. And because of all of these exciting opportunities, we're open source, which you can access here at this QR code. And with that, I'd like to thank you all for listening, and I'd be happy to take any questions.
interesting work. I'm Jing Li from Michigan State University. So when you're converting the surface normal to the surface geometry, do you assume the surface to have a smooth prior? So say what happened if the surface itself has like say a right angle sharp turn? Will your system handle this situation?
Yes, thank you for your question. That's a great question. So there's sort of scenarios we think about. If it's a sharp turn where we can reconstruct normals on both sides of the turn, then it would be able to successfully reconstruct this. The other part of the project, which I didn't have time to talk about today, is sometimes there's sharp turns where there's portions of the normals we can't reconstruct, a small part of the object that we miss. In which case what we do is we actually separate the object into different components and reconstruct each one separately so that we don't have errors which accumulate over the surface of the object for exactly the reason you're talking about.
Thank you.
Thank you, Laura, for the great talk. This is Shimin from Hong Kong PolyU. And I have a question that from your slides, your design relies on a high-dimensional antenna array for the millimeter wave. And my question is, have you tried any different sizes, like if we only have a 3+3 transmitter and the receiver, what is the will these impact the performance of your system?
Yeah, thank you for your question. So can we use a smaller array in order to reconstruct our objects? We haven't experimented with it yet, but it's certainly an interesting direction to explore. The main thing that happens when you reduce the array size is you lose resolution, but you also lose coverage on the normals that you can reconstruct. So thinking about how we can move from these larger arrays to much smaller ones, perhaps using machine learning to fill in the gaps, would definitely be very interesting future work. But the core underlying techniques should still apply in such a case.
Thank you for your answer.
Thank you.
Very nice piece of work and very nice presentation, by the way. I thought it was very well done. One question I have is, what happens if inside the object that you're looking, there are multiple objects there? The examples you gave were sort of single objects. Does the system, is it able to resolve it, or how does it work?
Yeah, it's a great question. So we operate with multiple objects. So far, we've shown a preliminary investigation into multiple objects with a fork, knife, and spoon, and some other results as well, which the objects are all together in the scene, but somewhat spaced apart. So we're still investigating an even more complex scenario where you have lots of objects piled on top of each other. So definitely something we're still thinking about.
A related thing is you talked at the very end, you started talking about, I think, when you mentioned things like machine learning, you wanted to go to first principles as opposed to machine learning. That's all fine, but can you, do you see an opportunity to use machine learning after you've done some resolution already on this? And then try to then further resolve it or get further information on the scene or object or something?
Yeah, a great question. So thinking about the ways we can use machine learning in combination with mmNorm, there's a few things we've been thinking about. One is to use the output of mmNorm as input into machine learning.
Yeah.
But the other is to actually leverage a lot of the insights from mmNorm and build that fundamentally into the way that we think about machine learning and whether we should be learning directly from the SAR image or learning from something closer to what mmNorm, the insights that we gain from that.
Okay, thank you. Very nice presentation.
Yeah, sorry, quick follow-up. Actually, you might be surprised, there are a lot of first principle-based software inside autonomous driving industry. They do this kind of stuff before machine learning model design. So, for example, LiDAR also has surface normal computed by the returns. I'm sure my friends in Waymo is very interested in this.
Yeah, of course. So, yeah, great point. So there's how is this related to other modalities and their use of surface normals? We definitely see surface normal estimation in things like LiDARs and cameras. One of the main differences here is that we have so much lower resolution in millimeter wave. It's not immediately obvious how you can estimate normals. It's not that you get a high resolution point cloud and you can immediately perform a standard normal estimation on the point cloud, we had to come up with a new method, a fundamentally new way of estimating surface normals using these millimeter wave signals, with hopefully the same benefits that we see in these other modalities.
Yeah, and I see huge potential because in latter case, surface normal is used in mapping, localization, detection. I'm sure millimeter wave surface normal can also be used for this, even there is some fusion potentials, right, between modalities.
Yes, we think there's many, many exciting opportunities, so I agree with you there, yes.
Hi, this is Guo Zhenzhu from Origin Research. This is really great talk and great work. I just have a quick question. Like, I'm wondering if the material of the object would affect the performance. Like, if it's a matte surface, like, will that affect the millimeter wave signal reflection? Have you considered that?
Yes, thank you for your question. That's a great question. So does the material of the object impact our reconstruction? And so in our experiments, we tested across a variety of object materials, including metal, cardboard, plastic, wood, and some others as well. We're able to operate across all of these different material properties. The biggest thing that we would see is a change in signal strength, SNR. So for example, a metal object will give you a stronger SNR than, for example, cardboard, but in our scenarios, we were still able to reconstruct these lower SNR objects like a cardboard box.
Oh, I see. How about the surface? If it's like a smooth surface, or if it's not that smooth, like it's matte surface, will that affect the performance?
Yeah, another excellent question. So how does the surface roughness impact the results? So this really brings us to the question of specularity versus diffusion. So we're relying on some level of specularity from the objects, which is the case for almost all objects at our millimeter wave frequency. So the specularity property depends on both the frequency and the material roughness. So at our frequency, the roughness would have to be around half a millimeter to see purely diffuse reflections, which is very rough for most everyday objects. It's not very common in most of our scenarios.
Oh, okay, thank you so much.
Just want to insert one more critical question. One question hasn't been asked is, in order for this to work for autonomous driving or any robotics real-time systems, what is the computation overhead? Right? How fast can you, I see you do reconstruction, but can you do imaging in real time?
Yeah, great question. So what is the computational overhead of our system? So the most important thing here is the computational complexity of our system, which we analyzed and included in the paper. And for the most part, most of the steps have the same computational complexity or even better than a standard millimeter wave back projection. And there's been many works on how to enable sort of real-time back projection. Since we're still using a prototype initial unoptimized implementation, it still takes around 30 minutes per step, but we definitely think a real-time implementation of mmNorm will be really exciting in the future.
Thank you.
Hi, this is Yadong from University of Washington. Very interesting work. I have a follow-up question regarding the different materials. So what if the objects are made of different materials? Let's say we have a knife, it's made of metal and a wooden handle. So can mmWave reconstruct both the metal part and the wooden part simultaneously?
Yeah, great question. So how do different materials in the object impact mmNorm? And so in our objects, a lot of objects do have different materials throughout the object. For example, the fork, knife, and spoon I showed you is not this one, but one that is plastic around the handle. And what is important here is that what we're trying to estimate is for a given point on the surface, which antennas are receiving the strongest reflection. So it's somewhat independent from other points on the surface. And we use the separability provided by the SAR image to sort of isolate these different parts of the surface so that they don't impact each other.
I see, thank you.
Thank you.
All right, let's thank Laura again. Thank you, Laura.